Welcome to the MSPPy tutorial series. In this video, I'm gonna give you an overview of the package and some of the key features. So MSPPy is a Python package to solve multi-stage stochastic linear programs. It is built upon the methodology that we've covered in the previous videos. So far, most of the other existing open source software packages are written in Julia. Comparing those with MSPPy, apart from the difference of the language choice, MSPPy is the first one to consider continuous data processes. Before the invention of MSPPy, the other packages often started with a list of scenarios or a Markov chain, which is called a discretized problem in our methodology, if you recall. But as I said, solving that does not provide the solution we really want. So MSPPy provides the all-in-one functionality that enables you to build and solve true problems in one interface. In addition, it also implements the rolling horizon algorithm and periodical SCDP, which are some important substitutes of the SCDP algorithm. On the other hand, those packages written in Julia have the advantage that they offer generic interface of a bunch of solvers. So you can use whatever solvers you want. So this is a cool feature and could be a future development of MSPPy. Now, just to tell you a little bit of structure, MSPPy is composed of 5 modules, and MSP class represents a multi-stage stochastic program, and SP class represents an individual stochastic stage problem. So you could imagine an MSP object is composed of a list of SP objects. And we have a discretized module to discretize a continuous process, and we have a bunch of solvers to solve the discretized problem. And in the end, we have an evaluation module to make policy evaluation. All right? So as I said, we have a standardized 4-step procedure to solve MSLP. And there are some variations for different solving algorithms. So now I will go one by one to show you exactly how those solving algorithms solve MSLP. So let's first look at SCDP. So this is just a recap. So SCDP leverages the convexity and iteratively update the approximation of the value functions. Again, the important thing here is that the cutting planes we obtain from solving the discretized problem implies an implementable feasible policy for the true problem. So in the end, this SCDP algorithm can solve the true problem. Okay? So here is the 4-step procedure to solve MSLP using the MSPPy package. So in the first step, we use the MSP and the SP modules to build our true problem. All right. Next, we discretize the true problem. If the data process is stage-wise independent, we can discretize it by sample average approximation. If the data process is Markovian, in some cases, we could add additional state variables and reformulate the problem to be stage-wise independent. A more general approach is to find the closest Markov chain to the Markovian data process as shown in this optimization problem. All right. Then we solve the discretized problem using SCDP or Markov chain SCDP. Since it's an iterative method, we need to have some sort of stopping criteria. So apart from some simple stopping criterion like time limit or iteration limit, MSPPy also provides you with some more sophisticated ones, including one based on optimality gap and another one based on stabilization of the policy value. In the end, we use the evaluation module to evaluate the obtained policy. Sometimes, if the problem is tiny, you can you can enumerate all the scenarios, and that'll give you an exact expected policy value. Oftentimes, the problem is huge, and you can evaluate by Monte Carlo simulation. So that'll give you a confidence interval of the expected policy value. And meanwhile, you can query some information, for example, the solutions of certain variables, the individual stage costs, and so on and so forth. So here's more details on how to construct the true problem. As I said before, if you use the package to solve MSLP, this is the step that you will spend most of the time in programming. All right. So we have added an additional variable zt being the local copy of xt minus 1, so that the state balance constraints are reduced to zt equaling xt minus 1. All right. And as a result, you are able to construct each individual stochastic models separately, and these state constraints zt equaling xt minus 1 will be added behind the scenes. Okay. After constructing those models, we need to incorporate the data process. Let's first assume the data process is stage-wise independent. In this case, we should incorporate the data process when we construct the SP objects, or individual stage models. So if it appears in the objective, here it is, it should be UT or VT, which means the related decision variables XT or YT have random objective coefficients. So we've overwritten the add var routine in Gurubi such that you can incorporate those random objective coefficients in the same time as you add those variables. The same applies to the data process appearing in the constraints. So essentially, the add constraint routine was overwritten, and we can incorporate them at the same time as we add those constraints. On the other hand, if the data process is Markovian, we add it directly to MSLP. All right? If your problem is mixed integer, you ought to use the so-called STD-IP algorithm, which sometimes requires you to binarize a problem. So we can have binarization as an additional step here. Okay. In the evaluation step, the obtained policy in this case is actually in the binary space. I mean, if you binarize your problem. So behind the scenes, the problem, the package will transform the policy into the original space. So this policy evaluation is still done on the original true problem, which is what we want. Okay? So, periodical SDP. I haven't covered this algorithm in the previous videos. If you're interested in learning more details, you can read our paper. But the essential idea is that for periodical problems, we can drastically reduce the number of stages by introducing a periodical analog of the dynamic equations, so that it avoids considering overlapping subproblems and remove the end of horizon effect. All right. So say your problem has a period m, then if you use PSDDP, there will be only m unique value functions. So in a backward step, we can now add cutting planes in a cyclical pattern. So from stage n plus 1 to stage 2, we solve all subproblems and add corresponding cuts to the previous stage. Besides, the cuts obtained from stage 2 is also added to stage n plus 1. All right. On the other hand, in the forward step, we use some heuristic to find trial points for stage 2 to stage n plus 1. sometimes it works better if you look at a longer horizon to generate those trial points than just looking at the first n+1 stage. For periodical STDP, we still use the standard 4-step procedure to solve the problem. All the steps are almost the same, but the difference is that we can specify different time horizon for the forward step, the backward step, and the evaluation step. So specifically, the time horizon we should look at in the backward step is always n+1, which is the period +1. But in the forward step, we could look at a longer horizon to generate trial points. All right, and we can also set the time horizon to be anything in the evaluation step, for the reason that what we have got from the PSCDP is an implementable feasible policy for infinite horizon. So it is certainly implementable feasible for any finite number of states. Okay. Now, for the extensive solver, the step of using that is pretty straightforward. Again, we construct the true problem, discretize the true problem, and solve the discretized problem. So there is no step 4, no evaluation step here, because the extensive solver only solves the problem for certain scenario tree. All right. For the rolling solver, again, we construct the true problem, but this time, instead of making discretization of the problem, we solve the true problem directly and make evaluation. But there's still some discretization going on behind the scenes. But for the users, you could just build a true problem and solve it directly. All right. So these are all the solvers we've implemented so far. In the next video, I will move to a Jupyter Notebook to show you examples on how to use the package.